now that's okay. Well, I think before we are all born, we are connected to our moms. Okay, and as soon as you are exposed to outside oxygen, the connection is severed, and the hole in the heart and the connectivity that you have, depending upon external circulation type of thing, it closes. Okay, but Mother Nature sometimes goofs up. Okay, and the so-called hole in the heart or the connections do not close. So the non-oxygenated mixture and oxygenated mixture, they mix with each other. That's why there's blue babies. Okay, so that's the things that now if I can zoom in on, see the circulation that we talked about, that occurs. There is something called the shunt between the pulmonary, that is the lung circulation, and the arterial circulation that mixes. So if the communication doesn't close, that's the cause for blue babies. And back in the 40s, lots of kids used to die from this defect. And Helen Taussig was one of the earliest pediatric cardiologists at the Mecca of American medical establishment. It's the Johns Hopkins Hospital in Baltimore. And she had the idea that, yes, if you could connect the two circulations, create a shunt, that would be the way to avoid, the blue baby syndrome. So she, she was a medical cardiologist, so she went to the surgeon and said, well, can you guys create a shunt? Okay, artificial shunt can you create? And the surgeon said, she went to the surgeons at Boston and said, lady, you're crazy. You cannot create a shunt like that, that would be against nature. But finally she was able to, say another surgeon named, Dr. Blaylock, who had moved up from south, and he said he agreed to create the shunt between the arterial and the venous circulation. And that was the pioneering of the first cardiac surgery. Now, true, it is not inside the heart, it is between two big pipes, the blue channel and the red channel, so to speak. So, but at least there was a start. And let's zoom in on this picture. So this is the normal heart, and there are several birth defects that are very common, which is like the two sides that I talked about, right side and the left side, and they are separate. But sometimes there's a hole in the heart, and that's, or the valve is narrow, so the pressure on the right side increases, and the blood flows backwards, just like your sink backing up, so to speak. So he agreed to create the shunt between the blue channel and the red channel. And this defect is fairly common, 1 in 2,000 kids. So you can say, this. And initially they just created a piece of blood vessel and connected the shunt. Now, this was one of the most pioneering surgery. And as you can see with the historical guideline, PDA ligation, the shunt was named after Blaylock and Taussig, Dr. Helen Taussig and Dr. Blaylock. And this is, if you are interested in history of heart disease, this is a famous story. There was a movie made after it. Now, Dr. Blaylock had an African-American surgical assistant, named Vivian Thomas. And Vivian Thomas was naturally talented, and he was actually better than, as good as the surgeon himself. But at the same time in Maryland, there was so much racial discrimination that in operating room, he would assist Dr. Blaylock, but he had to enter through the back doors. So there was, and there's a movie made after it, and Dr. Blaylock was from the South, and once Vivian Thomas was so good at assisting, he says, Vivian, this looks like something that the Lord made. So there was a movie made in 2005, portraying the story of Vivian Thomas, who assisted Dr. Blaylock in heart surgery. So it's free on YouTube. If you have an hour to spare, you can just look back at it. Something the Lord made, was starring I forget the actor. And now in the meantime, people were trying to, remember we talked about that if the heart stops, you've got about 4 minutes. So it was really hard to operate on a beating heart because you cannot actually stop the heart, because there are only 4 minutes. Now, one thing that is good about wars, that warts are good for surgery. Okay. And the first, and so bar fighting is good for surgery. So the first surgery that was done on heart was in 1893, when a guy was stabbed in the chest and he had blood filling up outside the sac of the heart. So the first surgeon in Chicago, he was also African American, named Daniel Williams, and he was able to put the stitch inside beating heart. Because as I remember last time I talked about, that people were afraid to touch the heart because it would stop. So that was the pioneering of heart surgery. Now during Second World War, there were a lot of projectile surgeries, and one of the surgeons named Dr. Dwight Harkin, he was absolutely disturbed by how these young people were dying of a missile, one direct hit to the heart, that the bullet would be sitting in their heart and they would be bleeding to death. So if there was a way to get it out, so he went to the military camp in England where he was stationed, and he appealed to his bosses, well, let me do something about it. Now, finally, reluctantly, they gave him a permission, and his first 14 patients died, but luckily they were all dogs. Okay. But so finally, he was brave enough that after he got enough experience to operate on humans, and that was a pioneering of, he was able to open the chest quickly and get the bullet out quickly in 4 minutes. Now at the same time, some people were experimenting that if you could cool the heart, it would have longer time. And there were some cowboy surgeons in Minnesota, and they were just trying to say, well, okay, well, how do we buy more time? So, well, can we connect another person to a beating heart and put like a live donor, say assisted circulation? Okay. So if a child has defect, they would ask the parent, if they have the same blood group, can we connect directly to the heart? And then that would give us a little bit more time to have assisted circulation. And they did several cases like that. Again, except for 100% mortality, they had at least 40% success rate. But again, that is far from acceptable norms. So at that time, people came up with the idea that can we cool down the body temperature? And so that was the start of heart-lung machine. And there were several pioneering, very well-thinking people that if they can oxygenate the heart outside, the blood outside, and filter, and at the same time cool down the heart, that would give us more time. And now the problem was, once you take the blood out, it starts clotting. So they had to put various blood thinners, and that took a surgeon named Dr. Gibbon about 30 years to complete. He started working on the heart-lung machine in 1930s, and it was delayed because he was drafted in the war. And so after the war was over, he and his wife, who was assistant, they started operating on people in Philadelphia, and they had 1 success out of 5. So he got a little bit disheartened and finally gave up operating on heart. But there are other people who took up the flag and went with it. Now at that time, again, how much help they got from engineering, that the IBM, which was International Business Machines, they had a lot of engineers who were able to work with the electrical pump and oxygenators. So they were able to help Dr. Gibbon. So there was collaboration between engineers and heart doctors for development of heart-lung machine. Okay, and so now just for sake of time, the other major problem was high blood pressure. Now, I'm not going to ask you if you recognize who this man is in the wheelchair. Does anybody wants to take a guess who is the president? The guy who was in wheelchair? FDR, right? Yeah, spot on. Okay. So when FDR was president for, he won like 4 times, I think, before they passed the law, but can only run twice. And when he had polio, and he was the most famous case for polio, but that's digressing. But when he was a president in 1943, his blood pressure was as high as 230 over 150. And you know what his doctor's advice was? You should take naps in the afternoon and cut back on smoking. And this was the leader of the free world. So how bad the treatment was at that time, because this is not that far back, in the middle of the 20th century. Okay, so this was another major cause for, now just recently it was in the news that one of the young actors, I think, had a stroke at age 52. Okay, I think he was on Beverly Hills 90210 or something like that, so this just shows how common the stroke is, because we're talking about, and so the treatment of hypertension started back mostly in the 1950s, and at that time drugs called beta blockers were discovered, okay, and that was the start of therapy for hypertension and heart disease. So another major problem, what is the biggest medical advance that took place during the Second World War? Anybody wants to take a guess? I'll give you a hint. Antibiotics. Okay. The biggest advance that occurred during the Second World War was penicillin. Okay. Discovery of penicillin was, and then we talk about, and the problem is just like over this weekend, I was reading this book about, antibiotic resistance. And this is a fairly good human interest story that one of the PhD researchers from UC San Diego had a totally resistant bug, and his wife, who was also a psychologist PhD, she goes, and he was going to die. The bug that he had was totally resistant to all the available antibiotics. And she finally researches on her own and goes on something called phage therapy. Anybody's idea what a phage is? P-H-A-G-E. These are viruses that kill bacteria. Now, in the Western world, we gave up on phage, but the Russians were smarter. They continued with phage therapy. So she contacted clinics in Russia and Poland, and they were able to devise individual phage therapy for this man, and she saved his life. He was in septic shock for 3 or 4 times and was dying. So it's a very nice human interest story as to how we had given up on a therapy as the viruses can kill bacteria. So that was one of the biggest advances that took place in the Second World War, was penicillin. Now, why is that important to heart disease? Because one of the common reasons for heart valve disease is not so much in the developed world, but in third world countries, was rheumatic fever. Okay, when or even here, when in the early 50s, people used to get strep throat, and with strep throat, the repeated infection, you get damage to the heart valves, and the heart valve, instead of being 3 finger breadth wide, becomes narrow, like instead of the size of a silver dollar, it becomes the size of a penny, and that can cause problems at very young age. So that's where we were getting to the second major part of heart disease was heart valve disease, back at least 30, 40 years ago. And again, there was no treatment. Even people as young as 30 would die of heart valve disease because of repeated bouts of rheumatic fever. From strep throat is dime a dozen, as you can see. Okay, now we've practically eliminated it because of availability of antibiotics. Okay, so people had the next step, logical step was, can we replace the valve? Okay, that's where it came into the mid-50s. People thought about, after the availability of heart-lung machines, to replace heart valves. Okay, now there were 2 people in Oregon, a young surgeon named Dr. Starr, and he was contacted by an engineer who had the brave idea of creating an artificial heart. But they thought that was a little bit too much to bite on at the first start. So they thought, instead, let's just settle for replacing the heart valve. So this is what a prosthetic valve looks like. Looks like, say, if you've seen kids yo-yo, how you blow on it and the disc rotates. So that is the initial valve was ball and cage valve. As you can see, it starts elastic, cage and a ball and valve, because this is simple hydraulics and fluid mechanics. Okay, how the ball goes up and down because of pressure differences. So it doesn't need any electrical or power source. The same way the disc rotates, just like as if you blow on it, type of thing. So a variety of prosthetic valves, it came into use. Okay. Now this ball and crush valve there was a big problem was it worked like a sledgehammer. It crushed all your red blood cells. So it caused clotting problems and you became low on blood count. So that's why this ball and cage valve is no longer used. Okay, let's see. So now the French were smarter, says, okay, well, I think because this valve needs blood thinning medicine, and you could, now if you're 30 years old and have an artificial valve put in, you need blood thinning medicine for lifelong. So that was a bit of a problem. So they came up with the idea, so well, can we put tissue valves, which are more biocompatible? Now, the most, now obviously you can't take valve from another donor, it's hard to do. Okay. So people came up with the idea of taking it from pigs. So the French were pioneers in using pig valves. And this is an example of pig valves. You can see how it is, porcine is pig valves. And the valve tissue was sewn on a, cloth or metal ring. And this is a variety of tissue valves that were discovered. So that was the one way of handling heart valve disease, and that became fairly prominent surgery in the 60s and 70s as to heart valve replacement. And now, and that required obviously open heart surgery, but now the technology has advanced so much that it can be closed just through catheters, and the entire valve can be replaced, both left sided. So a lot of medical residents are not going for heart surgery because the amount of work that they were doing has gone down substantially because it is replaced by, interventional cardiologists. Okay.
Did it have a high rejection rate? Because it's not even just a different human, it's a different...
No, it was, but surprisingly it was better tolerated. It was it was dead tissue, so no, there was not rejection rate. It was not a problem.
And did they have to use immune suppressors?
No, not at all.
Oh, no?
No, it was glutarate there was like a tissue, but it was not, living tissue, so to speak. So it was, they did not need any rejection phase. Okay, now I think, we're having a quiz on presidents. Anybody recognize this man? Okay, he was a former actor, but went on to become a president twice. He's Ronald Reagan. Okay, now he did commercials for cigarettes. So the biggest advance that took place was in 1960s for reduction of heart disease was the Surgeon General's warning of cigarette smoking. Now at the same time, people knew that back in 1940s, heart disease used to kill almost like 500,000 people in this country per year. It was one of the most prominent causes. And after the war, National Institute of Heart and NIH was funded. And the NIH funding went from 150,000 in 1945 to 40 million 10 years later. So that was the biggest advance in heart disease. Now at that time, epidemiology was coming into this thing. People wanted to find out what the risk factors for heart disease were. So there's a place in Massachusetts outside Boston called Framingham. So some of the epidemiologists, who work for NIH, picked Framingham, and they were able to convince the good people at Framingham to participate in the biggest long-standing prospective study of cardiac risk factors. And it started in the early 50s and has still continued, and it has generated almost like 12,000 to 2,000 papers from Framingham. Not only the first generation, but their grandchildren have been traced for risk factors. Initially, they just asked lifestyle risk factors, but then they started taking blood sample for cholesterol, and so the biggest advance that took place was to prove that cholesterol was a factor, diabetes was a factor, smoking was a factor. So all this data was proved in a prospective double-blind study based on Framingham study. Now, if you had a choice how not to pick parents, you don't want to pick parents who have genes for high cholesterol. As you can see in this baby, these little lumps, these are not tumors, those are cholesterol plaques. So sometimes kids have homozygous genetic defect where they cannot metabolize cholesterol. And while normal cholesterol should be less than 200, mean, some of these young people have cholesterol as high as 500 or 600. And they get heart disease at as young ages, 10 years old or 20 years old. Okay, so that's the homozygous, fortunately that's a fairly uncommon disease. But a lot of people can have heterozygous genes for cholesterol. Okay, if you give your blood sample to 23andMe, sometimes it's out, well, may show up, it says, yeah, you have the so-called ApoE gene for cholesterol. 1 copy or 2 copies type of thing. So that's a fairly common thing. Now for cholesterol also, a lot of work was done in Russia. Okay, the idea that cholesterol had something to do with heart disease was proposed as far back as 1913. Okay, and again, like I talked about, Framingham study, and then variety of receptors and other stuff were discovered back in the 70s, and this big fancy name, PCSK9. Okay, I'm not even going to try to pronounce the word, but those are the most expensive drugs that you see advertisements if you see watch regular television. Those are the newest kids on the block. They are injectable drugs for lowering cholesterol, and the cost of one injection is almost like several $100s. So it costs you in anywhere from $5,000 to $10,000 for treatment. But that's the latest gadgetry that we have for treating high cholesterol. And those are so-called monoclonal antibodies. So they are biologically designed drugs. So that's why they're so frightfully expensive. And these were the two guys who discovered the so-called LDL receptors, which are basically proteins in your liver that help metabolize cholesterol, the LDL receptor, and the various enzymes that are the rate controlling in the metabolic pathway for cholesterol. And by blocking these enzymes, we can help reduce the cholesterol. So those are the common drugs that you see ads on TV, that now they become generic, so they don't advertise that much, but there were drugs like Crestor and Lipitor and Mevacor that were advertised on, for lowering cholesterol. And they came out in the market somewhere around 1980s. And between quitting smoking and lowering cholesterol, we made a dramatic, remember the first graph that I showed about reduction of heart disease? So the two factors that have made a difference, by lowering cholesterol and reducing smoking. Now, Anna had asked me that I should put this slide of what are the warning signs for heart disease. So I didn't have that a few years ago, but these are some of the warning signs for heart disease. And you can see that they're a bit different in men and women. Okay, men are straightforward to figure out. They get chest pain, that grab the chest, goes down the left arm. But women are harder to figure out. Okay, as you probably know very well. They just get like unusual fatigue or chest pressure or anxiety or nausea. And so that's a difficult thing to heart disease. So that's why most cardiologists were men. So, they tended to underdiagnose or just say, oh, she's just a nervous woman, with anxiety or indigestion. So they were underdiagnosed. But now there are more women who are in medicine. If you go to medical school class, there are more women than men now. Okay. So that's why I think it's finally we are paying the necessary attention to women's symptoms in screening for heart disease. And again, like before we started, it came about that in men the heart disease has decreased, while in women it's slightly increased. Perhaps it's because of more awareness, or men who were smokers, they made a difference. So their heart disease has gone down. But women were never smokers to begin with, large numbers. So the numbers have, look kind of skewed when you compare the data. Now, how do we diagnose heart disease? We talked about symptoms, cardiogram, and the more important thing is blood tests. There are several biomarkers, like enzymes and proteins that have been released, even with the subtlest damage. Even if there is a small amount of damage, they can be diagnosed. And if you know that there were several companies, I think who have marketed the drugs for biomarkers, and there were sensitivities as high as 90% or 99% or so more. And this is one way to diagnose. You inject dye through catheter and see the coronary arteries, they light up. It's a nice, smooth-looking arteries that you can see. It doesn't take a PhD to diagnose that. It's nice and uniform. Okay. Okay. So this is called coronary angiogram. Now you can't just inject intravenous dye. You have to inject in the red channel, the arterial system. So you have to go backward, either from the groin or from the elbow, and thread a catheter across into the heart chambers and do a direct end-to-end injection and do angiogram that way. Now, this is again, you can see now this is a different picture. You can see the blockage here, and it is treated with, in the early days, we're treating the cause of blockage is two things: either a plaque from cholesterol, and on top of it, a blood clot forms. So we used to be able to dissolve the blood clot with enzymes and some expensive monoclonal antibodies called tissue plasminogen activators. So that was the early therapy of dissolving the clot. But then subsequently, people came up with the idea that if you can put in a little bit of coil, so we'll talk about the stents a little bit. Now, that's one of the most common reasons is blockage. Okay? But again, heart is an emotional organ. Now this is, you can get heart attack even without blockage. If you're under extreme stress, okay, like I briefly mentioned about, like during wars, during, hurricane or tsunami, or even if you look at, I had to look up on, Wikipedia last night that even simple things like emotional stress include death from loved one, okay, and this one can be very loud. Fear of public speaking. Fortunately, I don't have that, so I'm hopefully not going to get a heart attack within the next 1 hour. Okay. And arguing with a spouse, relationship disagreements, betrayal, financial problems. So all this can cause if you're under extreme stress. And I've seen, in my own practice, that women who had no blockages had heart attack. And this heart just balloons out. And this was described originally in Japan. And that's how this funny name came about, called Takotsububo cardiomyopathy. And what the word means in Japan is octopus pots. So when they go fishing, they use pots that look like this. So that's how the name came about. Leave your octopus in its Takotsubo. And now as recently as, and this fortunately recovers if you survive the initial heart attack. It gets better with time type of thing. The nerve damage is not, we may be left with some small scar, but it's not a permanent damage. So this is one reason why brain and heart are connected. Okay, so that's one of the rare causes for heart disease. And now, in the old days, we used to be able to diagnose pressure inside the heart chamber. Again, simple fluid mechanics. The right side is a low pressure chamber, so you can see the pressure wave is fairly flat. This is the right ventricle and various arteries, and you can see how the catheter is advanced and you can measure the pressure. Now, once we knew there were blockages, and this was the start of things, was bypass surgery. Most of you have heard of people having bypass surgery. That started sometime in 1967, and people took blood vessels from the arm or the leg and hooked up, it's just like basically hooking up the connection from just bypassing the blockage, literally. There's a blockage here, you hook up in another channel so the blood flows downstream. And bypasses can be single vessel, 2 vessel, 3 or 4. The maximum I've seen is as many as 9 bypasses in diabetic people, so it's a huge number type of thing. But the operation can be time consuming, there are risks. And the biggest risk would be infection and bleeding. And also, once you're on a heart-lung machine, your brain gets a little goofy, so even some smart executive who had bypass surgery, they would say, well, I'm not as sharp as I used to be, for at least several months. So there are several complications, And if you get into the problem of antibiotic resistance, we're going to be, have a real emergency as to how to treat these people who can get infections. Now, again, once if the damage is permanent, then not much you can do about it. Even the bypass surgery won't do any good. one of the few heart doctors that were on the cover of Time magazine was this prima donna guy from South Africa named Dr. Christian Bernard. In 1967, he first did the first heart transplant operation in Cape Town. Okay. Now, again, like how culture is tied in with heart. His second heart patient was a dentist, and his wife had a question, said, well, even if you do heart transplant, would he be able to love me like he used to love me before? So as to how culturally heart is tied in with emotions, So that was her main question. Okay. So now at that time, again, rejection therapy was rather primitive. So it had some drugs, but his success rate was rather poor in the early days and his second or third patients died of infections. Okay. So until people came out with the rejection drugs, okay, and first rejection drugs were discovered from a fungus on Easter Island. Easter Islands are in the middle of the Pacific, and people were looking for various antibiotics, and that's where they came up with a medicine called rapamycin or cycloserine. And there was some of the earliest, the rejection therapy advanced, made a big difference in heart transplant. But the big problem with this is we don't have enough donors for heart disease. Okay, I've signed my donor card, but fortunately or unfortunately, there's just not that many hearts available. Okay, so people back in the 80s, they tried with some artificial hearts, but again, the blood clotting problems and infection problems were a serious challenge at that time. And so people, a smart Swiss doctor had come up with the idea of putting in a balloon and a stent. Okay, we'll just move fast with this because I want to make sure we don't miss. And stent is a little metal coil that is inserted inside the blockage through the catheter, and that has reduced the number of bypass operations that were needed, type of thing. If you didn't put in the graphs, because they can be kind of boring, that the number of heart surgeries in the United States and all over the world has gone down, or the number of angioplasties or stents have gone up dramatically, type of thing, So, and this is where the engineering and material science comes into the picture. They are made of various alloys, stainless steel, cobalt, chromium, platinum, and with the stent, the big problem is scar tissue forms. So you need anti-platelet drugs that prevent scar formation. Okay. But that has been a big advance that has taken place. We'll just show you a little brief video of see the blockage there, type of thing. Can you hear it okay? The volume is... Okay, you can see now easily that the blockage that was pinched, it was like a pipe that was pinched, and that's been opened up with a stent. And just to prevent, the stents are coated with anti-rejection, with the drugs that will prevent the scar tissue.
Why doesn't the damage the
It-
but it's so
what-
narrow.
Yeah, well, there is some garbage that goes downstream, so to speak, So there is, small amount, it's like when you look at it, it's a pretty crude procedure. You're breaking the plaque, so to speak, but body,
Moving it.
yeah, so it's just, like we're dilating the blood vessel and some garbage that goes downstream, so to speak, Okay. And so there is some microvascular damage, but relatively small, so the heart is able to tolerate it, so to speak, And so it's, on one hand, it's kind of a crude procedure, because that's why the scar tissue forms, You don't build up cholesterol plaque very quickly within the first 6 weeks, but you could develop scar tissue, so that's the big problem. And you can see how small the stents look like. They're this small, Now, they look like a little metal coil, which you see inside your ballpoint pen, but they cost about like $10,000 or more. And yeah, I did have a slide of, like how the number of stents have gone down while, the number of stents have increased over the number of years. Now, these are some of the, now we talked about, I think I'm going to skim over some of these because these are some of the surgeries for children as to see various grafts are taken. And these are made of Gore-Tex and rings, so but I think this is for the sake of time. And these are the various catheters which are used for heart surgery. You can see how there's a balloon, they have curve, they have loop, all different shapes of things, so it's a lot to do with material science. And you can see them, there are different types: straight, curve, flow rate, side hole, end hole. Because to measure pressure, we convert potential energy into kinetic energy, so to speak. So that's how we can record pressures from the catheters. And again, these are some of the birth defects, which I think we won't dwell too much into it, But some of the birth defects can be treated with artificial things like coils. You can see how various coils are placed in to help Mother Nature, so to speak. And so these are some of the advances that have taken place in pediatric heart surgery. So the material science that comes into picture are various alloys of nickel, titanium, and these were designed earlier for the Navy, for submarine, but they didn't work for the Navy, but people started making these devices that help with the coil. Now, I talked about that this is, I briefly mentioned, that this was one of the NFL players named Teddy Brucci, and he had a stroke at a very young age, and this was one of the reasons. He was born with a birth defect between the right and top chambers of the heart, and you can see how the blood clot can travel from right side to the left side. This is the example of the blood clot, and if it breaks loose and goes to your brain, that can cause a stroke. And now, fortunately, he was in Boston, and he was taken to a major hospital, and they were able to plug in the hole by putting in a little umbrella-like device. If you go to a Chinese restaurant, you see how I have a fancy drink with a little umbrella. Okay, so that umbrella is inserted from the right side of the heart. It is advanced to the left side, and you pull it over so it occludes the hole. So pretty neat way of, plugging the hole in the heart without open heart surgery. So these are various catheters that are devised. Check something first. Let's make sure my volume is. Oh yeah, it is. Okay, we're back in business. So I think now, because sometimes when you're waiting for transplant, there were various assist devices that were devised, and you can see how there's artificial pump that is connected to the tip of the heart, and the whole circulation is bypassed, and an assist device takes over. This is so-called bridge to the heart, bridge to heart transplant. Okay, they're called left ventricular assist devices. Now again, biggest problem is infection and clotting. And the most recent listing is a robotic sleep over the heart. Okay, I think we have to listen to this.
Heart problems.
Prince later learned he would need a heart and lung transplant, an extremely complex and risky procedure. Plus, he would have to wait for not one, but 2 donor organs. His case was evaluated by hospitals around the country. No team of doctors would take it on.
At that moment in time, it was like I just gave up for the simple fact that it seemed like what nobody really cared.
His diagnosis too complex: severe cardiomyopathy and pulmonary hypertension. 2 conditions doctors often see separately, but almost never together.
It's either accepting death or going for this high-risk case.
Medical College of Wisconsin doctors at Prater Hospital decided to try something that had never been done.
So it was like a miracle because it's like just a couple of weeks ago they were speaking of death, and now they're coming to me speaking of life.
A procedure to peel out the clots from Prince's lungs called a pulmonary thromboendarterectomy, or PTE, and implanting a total artificial heart.
The first thing you're doing is you're making a fairly major incision. You're cutting the chest open. For a lot of people, that's a big deal. I mean, that's open heart surgery. It's a real operation. Then you're putting the patient on the heart-lung machine, and you're actually literally cutting out the heart. So that's a pretty big deal as well. But then you're cooling the body down, and you're stopping the circulation for 20 minutes at a time and digging all these clots out of the lung. And if you get in the wrong tissue plane, that could be a life-threatening event. Then you're sewing back in an artificial organ that's going to completely replace the function of the human heart. And then finally, you're separating from the bypass circuit, you're closing the chest, and you're heading up to the ICU. When you put all that together, I truly believe there is no more complicated or high-risk procedure that a human being can go through than that.
Few centers in the world have the surgeons trained to do these procedures. Prater Hospital does. Medical College of Wisconsin doctors Lyle and David Joyce, a father-son duo.
We work together just like the right hand and the left hand.
Dr. Lyle Joyce was on the team that implanted the first permanent artificial heart in 1982.
Very few people at my level have a mentor who they operate with, who can teach them these things, and who has had the depth of experience that he has to be able to, offer that to their patients as well.
The Joyces gave Prince hope.
I'm like, hey, we go fight it out.
With Prince's blessing, the team got to work.
Everybody that was going to be touching that patient sat in the conference room. We pulled up pictures, we looked at all the different scenarios, and we walked through the operation. We lived that operation step for step.
The surgery was on October 20th, 2017. After roughly 6 hours in the operating room, Prince had a new total artificial heart and healthy lungs.
I believe that Dr. Joyce's and the whole cardiologist team gave me a second birthday.
Thanks to the PTE, Prince no longer needs a lung transplant, and the total artificial heart will keep him alive until he can get a heart transplant.
It feels like a machine pumping in your chest.
The drag lanes come out right under the rib cage on the left side here, and it's a hose that
Stops. Sorry about that. I think there's a glitch here. It talks. It's a little longer, but it tells you about the more details of the device type.
Heart problems.
Now, I think so this is again. We talked a few minutes ago about the shortage of organs. Okay, just like with the valves. Now, I think after 50 years, we've come around and said, okay, well, let's go to our friendly animal again, pigs. Okay. Now, can you get the heart from the pigs? But pigs have a problem. They harbor all sorts of viruses. They're not the cleanest animal in the world. Okay. So now, I think now removing the pearls. That's not what the pearls that you may think about. I know it's a pig retrovirus. Okay. Now, I think you have to listen to this. That this is one of the biggest guy in genomics is a guy who is larger than life named George Church at Harvard. He has a big lab, in genomics and longevity.
Can I make changes
This is one of his
in a
PhD
human
grad
cell
students.
using a tool you may have heard about called CRISPR? We were one of the first two groups to report the successful use of such a tool in changing our DNA. It was an exciting moment in scientific discovery. The gene editing tool CRISPR has two components. It has a scissor called the enzyme CRISPR and what is called a guide RNA. Think about it as a genetic scissors with a microscope. The microscope is a guide RNA which brings the scissors to the place we want to cut. And it says, here it is, and the enzyme CRISPR just cut and repair the DNA in the way we want. Shortly after we reported our study, physicians at Mass General Hospital were intrigued by the medical applications of our research. They reached out to us, and together we began to see the potential to use CRISPR to solve the organ shortage crisis. How do we do it? It is simple, yet very complex. We started by making changes in a pig cell to make it virus-free and human immune compatible. The nucleus of that cell is then implanted into a pig egg and allowed to divide into an embryo. The resulting embryo is then placed into the uterus of a surrogate mother and allowed to divide into a pig. Basically, it's a process of cloning. The piglet then carry organs whose genetic makeup hopefully wouldn't be rejected by the human immune system. In 2015, our team decided to tackle the viral transmission problem first. We wanted to take out all 62 copies of the Pyayt virus from the pig genome. By that time, it was nearly mission impossible. Even with CRISPR, we could only do 1 or 2 modifications within a cell. The record for number of modifications we can do in a particular cell was 5. We had to increase the throughput by more than 10-fold to achieve that. With very careful design and hundreds of trials, we successfully took out all the virus, broke the record. More importantly, our study showed that we could eliminate the possibility of this dangerous virus being transmitted into humans. Last year, with a modified cell and cloning technology, our startup, eGenesis, produced Leica, the first pig of its kind born without birth. Leica represents the first critical step in establishing the safe xenotransplantation. It is also a platform that we can do further genetic modification on to solve the immunology problem. Since then, we have created more than 30 pigs without birth, and that may be the most advanced genome-modified animal living on Earth. We named Leica after the Soviet dog, who was the first animal to orbit the Earth. We hope Leica and her siblings can lead us into a new frontier of science and medicine. Imagine a world where patients can
So you get the idea as to how they are tackling the problem with organ storage. So the big advance that is going to be is the genetic and tissue engineering, and this was that's an Intel Science Talent Search, and this young girl who is only 17, she got the award for now doing surgery on a fruit fly heart, basically. Now you can imagine how small the fruit fly heart is, and this was her project about removing the beating heart analysis and modifying the several transcription factor proteins. Okay. Now, I think let's move one forward type of thing. Now again, like we talked about, everybody knows about the genomics of sickle cell disease or the single cell diseases, like that. But when it comes to heart disease, it was almost like trying to find a needle in the haystack. Okay, and finally, with big data analysis and increasing the sample size, people are able to, come up with so-called polygenic scores for heart disease. As you can see, variety of markers that have been selected, and now.
Good afternoon and welcome to the 45th annual James Hart
I think this is a lecture. No, now I don't know how many of you have taken genetics or genomics classes. Anybody? Okay, all right. With the Human Genome Project, one of the main scientists who work with him, his name is Eric Lander. He's at MIT, and he was pioneer for heart disease. And once, to be able to go. This is a long tape type of thing, so I'll just send out the link to this. And he talks about how everybody else had given up on trying to find genetic markers for coronary artery disease, but the people at MIT, they knew more math than other universities, so they increased the database from anywhere from 1,000, genomes to as many as 50,000. Okay, and finally they were able to come up with genetic markers based on so-called polygenic score for coronary artery disease. So this is a talk, by Eric Lander that I think if we have time, I'll have it separately on the other part. So he talks about the markers that have been discovered for coronary artery disease and for heart rhythm disorders such as atrial fibrillation. Okay, now we talked about ventricular fibrillation last time. Now one of the common rhythm which can cause stroke is called atrial fibrillation. He said instead of the bottom chamber, it's the top chamber that's quivering. Okay, like top and bottom should be in sequence. But if the top chamber is quivering like this, like a bag of worms, that's one of the other common reasons for strokes. And this is where you give shocks to a person who is wide awake, and you have to put them to sleep, otherwise they will kick you when they are, finally if they get up. So this is called cardioversion. Instead of defibrillation, the names are different. This is done under planned setting. You put the patient under sleep for 5 minutes or so, and a precise shock is delivered. As you can see how the abnormal rhythm is converted to normal. Okay. So again, like when we again wanted to reemphasize the point with sudden cardiac arrest, the urgency of treatment is important. Time is money when it comes to heart disease. If you miss the 4-minute window, then your success rate decreases by 10% every minute. Now, one of the things done is, if people don't wake up after cardiac arrest, sometimes that's done, is medical hypothermia. You cool down the body to about 79 degrees Fahrenheit for about 24 hours. And people are not sure as to how that works, but that improves your chance of brain recovery. Because the biggest problem that occurs with heart disease is sometimes, your heart beats, your lungs work, but your brain doesn't wake up. So you are basically creating a heart rhythm, a functioning person who is somewhat brain dead. So this is one of the big ways to, okay, now I think, now again, I think, this is one way of optogenetics is, I think Anna has worked a lot on optogenetics, so I had to work hard to find this slide about hybrid bioelectric system for restoring regular rhythm. Okay, let's see. And this is animal work, as to how the heart rhythm is implanted, and light reflector source is implanted, and it spontaneously detects rhythm and delivers a pain-free shock. Because when you give the shock, that hurts like heck. When you're transmitting at least 400 joules of electricity to the heart muscle. So this is one way of avoiding painless shock, because the light source delivers precisely the shock type of thing. So this is about as recent an article as I could find. As you can see, the source is from Translation Medicine, February of 2019, optogenically modified heart. Okay. And again, we have smartphone devices and various sensors. So based on the stent, because remember that stents can narrow up, and randomly at 6 weeks or 6 months or a year. So people are discovering are working with something called smart sense, which have sensors that wirelessly transmit signal of pressure differences across the stent to alert the development of a problem. So this is the new things that is coming down the pipeline as to how pressure is monitored across the heart, and based on the pressure difference, the stent actually transmits the information to the physician or to the clinic to see if there is difference that is developing, the stent is developing a problem. Okay. The best advice to prevent heart disease still remains: do not smoke, eat right, exercise, learn how to relax. If possible, pick right parents. Okay. And if those of you who really want to read about heart disease, this is a recent book written by a cardiologist about heart history by a guy named Sandeep Jauhar. And it's a nice, easy reading, if you still read books. Last but not the least, some people are just born lucky. Okay? And so this is, future depends on all of you. I think I skipped some of the slides because I wanted to make sure we cover all the time. Okay? And all right, so I think we're done. And if I can see if I have the time to show. Okay, yeah, I think. Now my other big interest is now I'm on a genomics kick, so I think it's fun to listen to.
Wasn't significant to figure out how much.
We just have 4 or 5 minutes of listening about his
It was a
land
lot.
justice.
By today, something like 50% of all the current these diseases can be explained based on genes.
Oh.
So anyway, the pendulum swung back to non-genetic genetics. But wait. Let's not give up on those.
Oh, it's not very much on. Okay, I think I'll just have to send this out. I can't duplicate it very easily. Somehow it's not extending. Okay, so any questions or comments? I think I'll just send out the video to, I think if you have time, if you can watch it type of thing. So he's one of the gurus of genomics, and is an amazing teacher. So if you are ever interested in class, he teaches a class at MIT about, early genomics type of thing. It's a fascinating class that, even though he's a world-renowned genetic expert, he teaches Genomics 101 at MIT. So it's a fun class to listen to. Okay, all right, folks, I think we're done. If any questions or comments, I think we're done a little earlier than expected. But I think, instead of keeping you longer, you can always think of better things to do in this meeting.
Thank the speaker, and then